has started.
Welcome back. Before today's lecture, one announcement regarding the in-person session on Thursday. To fulfill the hybrid requirements by the school, we have to do this in-person meeting on Thursday. So we are going to meet at Vanilla C 340. To satisfy the social distancing, the first meeting only invites 1/3 of the class, whose last name is from A to H, and the students must wear the facial mask, and also students must sit apart. If you are within A to H, and if you wish to come to the classroom, please email me before Thursday, so I could have a head count in advance. So this in-person meeting is optional, and we will use the same Blue Jeans link to broadcast online at the same time, and also we will record it for later YouTube release. The agenda of that meeting is to review and solve the practice exam that is available under the exam folder in the Canvas. And one more reminder is on the homework 2 that is due this Friday midnight. All right, any questions? If not, then we can start our technical discussions today. So this is the Lecture9, and we are going to discuss the MOSFET IV characteristics. So basically current versus voltage. And this is part 1. Here is a reference chapter and the recorded lecture from the last spring, and also Professor Asif Khan. So let's have a quick review of the MOSFET structure. We have shown this slide in the lecture 7. And here this is a three-dimensional view of the MOSFET structure. We have the gate, and then we have the oxide, which is insulating, and then we have the substrate of the silicon at the bottom. And then we have the source and the drain doped. So in the NMOS we are going to discuss today, the substrate is p-type, and source and the drain N+ doping. N+, this plus means heavily dope. The doping density is high. This is to make a good contact for the metal interconnect. So this is the MOSFET structure, and then we defined two geometry parameters here. One is L. This L is the distance between the source and the drain. So we call this length of the gate. And then on the other dimension here, we have the W. That is the width of the gate. So later you will see that the L and W will determine the current of the MOSFET. So here we define the L and W first. So this is the circuit symbol for the NMOS. We have a gate and a drain and source. And then this is a cross-sectional view of this MOSFET structure if we look from the side. And again, this is a p-type substrate, and then the n-type source and drain doping. Then we have voltage to be applied to the gate and the drain, and typically for the NMOS, the source is grounded. So later we are going to apply the drain voltage and the gate voltage and the drain voltage. So the gate voltage and the drain voltage will determine the current flowing to the drain, and that current will be synced to the source. So today the major task is to derive this drain current as a function of the gate voltage and drain voltage. Okay, so any questions here? Alright, so this is NMOS, and in the lecture 10, we are going to discuss the PMOS. But today, let's focus on the NMOS. And remember, NMOS built on the P-type substrate. Why is that? Because later, as we increase the gate voltage above the threshold, then operate the inversion charge. So the surface will become N-type. And then we will rely on the electron flow in the NMOS to conduct the current. So that's why this is called N-type MOSFET. Okay, so let's look at what's going on in the MOSFET. And let's take NMOS as an example. So in the lecture 8, we discussed about the MOS cap, MOS, but without the source and drain. So it's a capacitor structure, and there's no current flow. But today we are going to add this source and drain. Then we can have the current flow between the source and drain. But let's review what's going on here. Let's say if we assume the drain voltage is 0 to start with, and we only apply the gate voltage Vg. So this is similar as a MOS cap in the last lecture. So as we discussed before, when we apply the gate voltage larger than 0, in this case, the positive voltage on the gate will repel the holes from the substrate away. So after the holes are pushed away, then this is a depletion of the P-type substrate to the surface. And then as we further increase the gate voltage, we increase this further, then the depletion width will further increase. So this is what we discussed in the lecture 8. And then if the gate voltage is larger than this threshold voltage, the surface of the silicon is inverted from the P-type to N-type. And in the strong inversion condition we discussed earlier, we are going to have electrons towards the surface. And this layer of electron is called channel in the MOSFET. So this is like a channel between the source and drain. Why is that? Because source and drain, is N-type. So source and drain already have a lot of electrons. Now you create a layer of electrons like a channel to bridge the source and the drain. Now if you apply the drain voltage larger than 0, then these electrons can flow. So you conduct the current. So let's look at this animation. Now we have the Vg larger than threshold, so we'll create this layer of inverted electrons. We call it channel. And then now we apply the drain voltage larger than 0. So that means here we ground it, and we have the positive drain voltage towards the drain. So let's look at this animation. So here you have electrons, and the electrons can move under the electric field. This is due to the drift. And then the electrons will move in this counterclockwise. This is because electrons go to higher potential, right? So the drain is higher potential. So from the channel, so electrons will move from the source to the channel and then back to the drain. So that's why here the left-hand side is a source, because it provides electrons like a source to the channel, and then the electrons are connected to the drain. So that's why this is the source and this is the drain. Okay, so you may wonder then why the left-hand side is source and right-hand side is drain. Actually, this is not always true. So what matters here is the voltage potential. If you look at the MOSFET structure, let's use this symbol, circuit symbol, to represent the MOSFET. So in our example, we say the left-hand side is source, right-hand side is drain. But this may not be always true, okay? So it doesn't matter which, let's say, source and drain. If you think about this structure, it's a symmetric structure. So which is the source and which is drain can be always exchanged depending on what? Depending on the voltage you apply. So in the NMOS, we always define that the lower potential is a source and higher potential is a drain. This is because, as we said earlier, the source provides the electron and that is grounded. And then the drain will collect the electron because the electron go to higher potential. So drain must be positive voltage. So then in this example, then we have the left-hand side to be source, right-hand side to be drain. But if you change the voltage you apply, you can apply the drain voltage to the left-hand side, right? So let's say you apply the drain voltage to the left-hand side, then the left-hand side becomes a drain, and then if you ground the right-hand side, then the right-hand side becomes a source. So the source and the drain, can be changed depending on the voltage you apply. So any questions here? All right, so let's look at the diagram here. So this is above the threshold. When the gate voltage is larger than threshold, then we'll create this channel, and the channel is by this inversion layer, mobile charge, and in the NMOS, that's electron. But under the channel, we still have the depletion region. That is a fixed charge by the dopant, and in this case is the acceptor, p-type, and it's Na and also minus. But the fixed charge cannot move, okay? Only the free electron can move under the electric field. And in this case, then the electrons move from the source to the channel and then connect to the drain. So you can see that before the threshold, let's say the gate voltage is small, then you don't have the channel. Then even you apply drain voltage, the current should be very small. So it's like the MOSFET is in the off state. But when the gate voltage is larger than the threshold, then we create this channel. And now if you apply the drain voltage, then the current can flow. So in other words, this MOSFET is like a gate-controlled current switch. Why is that? You first need to look at the gate voltage. Use the gate voltage to turn on and turn off. If the gate voltage is smaller than the threshold, then it's like off state. And drain and source is more like an open circuit, no current flow. But if the gate voltage is larger than the threshold, we create this channel, and now if you apply drain voltage, then the current can flow. So the current, whether flow or not, depends on the gate voltage. So That's why this is a gate-controlled current switch. So the switch has off state and on state, and then the control is done by the gate voltage. So this transistor is a building block for all the circuits today for the digital computing. And basically 1 and 0, the switching is controlled by this on and off of the switch. Any questions here? Okay, then next we are going to derive the IV relationship. We want to know what is the current given the gate voltage or the drain voltage. Before we derive that, let's look at the charge distribution in the channel. So here let's talk about the x direction. So in this example, we are going to use this vertical direction as x. This is a little bit different from the conventional definition, but let's do this way. So let's look at the vertical direction as x, and this vertical direction is essentially the MOS, faster direction. And then we define the horizontal direction as the y direction, so that is the channel direction from the source to the drain. And then we want to look at the charge distribution. So that is the mobile charge, which is the inversion charge. And in this NMOS case, the inversion charge is the electron. So we want to know the free electron density along the channel from the source to the drain. First, let's look at the drain voltage equals to 0 case. And this is more like a MOS cap. If the MOS cap, let's say gate voltage larger than the threshold, then we already create the inversion charge, and we have this channel. But since the source and the drain both are 0 voltage, there's no difference. So the charge along the channel should be uniform. Okay. So here we show the inversion charge, and it's negative. So we show the axis pointing down for the negative charge. And then this negative charge density should be flat or uniform across the channel. So here we have the 2 points. One is y equals to 0, that is the starting point here for the source end. And then here y equals to L is the ending point, that is for the drain. The L is the distance between the source and the drain, that is the L of the gate, or sometimes we call it L of the channel length. And the inversion charge density here is given by this formula. This is from the last lecture. We talk about when the gate voltage is above the threshold. If you have additional gate voltage, this additional voltage will introduce more inversion charge. So the charge density is given by, let's say, the capacitance of the oxide, COX, multiplied by the voltage. So you have gate voltage applied. The gate voltage first need to overcome the threshold voltage. So it's Vg minus Vt. That is the additional charge you create after the threshold. And then this capacitance times the voltage. Okay. And then we need to times the W. W is the width of the transistor, because here we only show the two-dimensional cross-section, but actually the transistor will have the third dimension, as we show in the previous slide. Like this, we need to think about the third dimension. So we only show the two-dimensional schematic. So that means we are looking at the density along, let's say, along this W direction. We want to squeeze that into a two-dimensional space. So if we have a larger W, we are going to have more charge in this two-dimensional cross-section. So that's why we need to multiply by the W. It's here. So by the way, the COX is the gate capacitance per unit area. So this one is the total gate capacitance divided by the area of the gate, that is W times L. So this is a definition of the COX. And this is uniform, so it's the same towards the source and towards the drain. Any questions here? Okay. Now let's look at when we apply the drain voltage larger than 0. Now we apply drain voltage larger than 0. Still here the gate voltage is larger than the threshold. So we have the channel, but now we have the drain voltage. The drain voltage will be dropped across from the drain to the source. If you think about the channel potential, the source side is grounded, so it's 0 voltage. And then here you apply the drain voltage to the right. So here you have the drain voltage Vd. And along the channel from the drain to the source, then the voltage will drop from Vd to 0. So the channel potential is non-uniform in this case. As a result, the inversion charge density will be non-uniform as well, because the charge density depends on the voltage difference between the gate and the channel. So the voltage difference here. Let's look at the drain side. Y equals to L at this point. What is the voltage difference here? So you apply gate voltage, and the gate voltage should be uniform. And let's say that towards the drain side and towards the source side, you both have Vg. It's the same terminal. But the drain side here, at this boundary, this voltage is provided by the drain voltage. So you have the difference only Vg minus Vd now. Towards the source side, you still have the Vg minus 0. So that's why you still have the Vg. And then this voltage needs to overcome the threshold voltage as before. So you still need to minus the Vt for both cases, for both source and drain. So then this is the effective voltage across the MOS structure from the gate to channel. And now you see that this is non-uniform, and you see that towards the drain side, because the drain voltage raises the channel potential, the voltage across the oxide becomes smaller. So the inversion charge density also becomes smaller. So here we show the inversion charge density becomes smaller. This value becomes smaller than the source. As you can imagine, when you further increase the drain voltage, then this charge density will become even smaller. Okay, so this is what will happen in the channel when you apply the drain voltage. Now we want to derive the current, drain current. So how do we get the current? We can look at the middle of the channel here. Remember, the current always determined by two factors. One is how many charge are there. The other one is how fast they move. So if we look at the middle of the channel and we think about the cross section, so here we draw the third dimension, that is the W dimension, the width. So think about this is in and out of the plane. We draw it the third dimension here. So if you think about there's a cross section in the channel, and if we know the charge on this cross section area, and then how fast they move, then we know the current. These electrons move across this cross section. So the current is continuous, okay? No matter where you cut this, okay? The current will be the same because current needs to be continuous. So let's do the middle because we want to take the average. So the charge average is the average of the charge at the source and the charge at the drain. So basically it's the average of this term and this term. So that is the average charge. And then the current is how many charge there and how fast they move. So how fast they move. If you assume they have velocity v, then your current is essentially how many charge and how fast they move. And the electric, let's say the velocity v depends on what? This is a drift current. You have the drain voltage, external voltage. So this drift, if you recall, the absolute value is the mu E. What is mu? Mu is the mobility. E is the electric field. So this is from the lecture 6 on the drift currents. Velocity is proportional to the electric field and the mobility. And this is for electron. So it's mu n. And then what is the electric field E? The electric field on average in the channel is the drain voltage divided by L by definition, right? So you have the voltage across the channel. Then the channel distance is L. So the average electric field should be Vd divided by L. So you will get the drain current if you plug in all the terms here. So let's do that in the next slide. So this is what we discussed. So we first get the average charge density, that is the charge density from the source and then from the drain, and then you have those two equations, and then you take the average, you will get this equation, and then this average charge and how fast they move given by the drift, and then electric field E is Vd divided by L. So you plug in the Q average from the previous slide, then eventually you get this equation. And let's rearrange some terms. Typically we want to move those mobility and L in front. Then eventually we get this in this box. So drain current equals to mu n COX W over L, and then multiply by this voltage terms. So the voltage terms here have Vg minus Vt times Vd minus half Vd square. So this is IV equation we want to derive. And the key, as we mentioned, is the Q average times the velocity. which is given by the drift mu E. So here this term, so here we have some coefficient in front of the current, and this depends on the mobility, the capacitance of the gate, and this geometry parameters W and L, that is the width and the length, as we show in the first slide today. And then the voltage term. So the voltage term, there are two voltages here. Actually, yeah, two voltages. One is gate voltage, one is the drain voltage. Of course, you have the threshold voltage, but that is determined by the doping, as we discussed in the previous lecture. So what you can control as a user is the gate voltage and drain voltage. So this drain current is determined by both gate voltage and drain voltage. Any questions? So let's continue. This IV relationship is in the so-called linear region. And next, we are going to derive the saturation region currents. And we will discuss why this is called linear and why this is called saturation later. So the linear region is where the channel still has some finite charge density was a drain like this. But as you can imagine, if you further increase the drain voltage, the charge density towards the drain will further decrease. And eventually, it will decrease to 0. And we call this pinch-off condition, when the charge density at the drain side equals to 0. So that is this one equals to 0. And then eventually is this voltage term equals to 0. So you can rearrange that. This is the drain voltage equals to Vg minus Vt. So before pinch off, the drain voltage is smaller than the Vg minus Vt. But after pinch off, the drain voltage is larger than the Vg minus Vt. So this drain voltage at this turning point is called the Vd set. The set is the saturation. So it's the drain voltage before entering the saturation point, saturation region. So why this is called saturation? When the Vd is larger than Vg minus Vt, this is called the saturation. This is called the saturation. And here we have this turning point, Vd set. The reason is that now here the electron density goes to 0, but still the current is flowing continuously. As you further increase the Vd, the current will no longer increase. It's like a constant above this turning point. Why is that? Because you need the electrons being collected by the drain. But now if the drain voltage is large enough, then the electrons available here will no longer increase. So the current will be saturated. Saturated means that the current will be a constant value, even when the voltage, drain voltage increases. So this is called the saturation, because you don't have more electrons available in the channel we connected. Remember, the current depends on how many electrons and how fast they move. Now, since the current, the charge density goes to 0, then you don't have more electrons available. Then the current will be a constant. Okay, so any questions? Okay, let's have a summary here. And this is the IV equations we will use over and over in this course for the rest of the semester. And those are very important, of course. So here we have three regions for the transistor's operation. First is the so-called cutoff region. This is before the channel is formed. That means the gate voltage smaller than the threshold. We haven't created the inversion of the channel. Then we don't have current, even you have the drain voltage, because the current is not formed yet. So the drain current is almost 0. And we'll talk about whether this is exactly 0 or not in the lecture, I think lecture 11. So, but approximately this is almost 0. And then in the linear region, or sometimes we call it triode region, this assumes the channel is already formed. So you have the Vg larger than threshold already. But then we need to determine the drain voltage. If drain voltage is small, let's say smaller than the Vg minus Vt, this is in the linear region, and then the pinch-off point not achieved yet. So we have this IV equation as we derived it from the earlier slides. We have this term here, a little bit complicated, but this is the IV equations we have. And then if the Vd is larger than this turning point, Vg minus Vd, Vg minus Vt. So Vd is larger than this Vg minus Vt. The transistor will enter the saturation. And at this saturation point, this turning point, we can get the current equation like this. How? We can plug in the turning point condition, which is Vd equals to Vg minus Vt. This is the turning point. And we can plug in this back to the equation in the linear region. Then you will get mu n cox w over L, and then Vg minus Vt. And at this turning point, your Vd now become Vg minus Vt, and then minus half Vg minus Vt squared. So you look at this. This Vg minus Vt actually will be squared here. This is next squared. And you have 1 squared minus half squared. So you will remain half squared. So that's how you get here. So the current will remain this value, even when the Vd is larger than the Vg minus Vt in the saturation. So this is called the saturation current, this one, ID set. When you plug in the Vd set equals to Vg minus Vt into the linear equation, then we can derive this ID set. So you see this is no longer a function of the VD in the saturation, because the current only depends on the gate voltage. We don't see VD here. That's why it's a constant regardless of the VD. And also this is a square term, so sometimes we call this square law model. So this is the first order model, the simplest equation for the transistor, and it's only good for the non-channel device. Non-channel means the L is much larger than, let's say, 100 nanometer, or even, let's say, even to the 1 micrometer scale. Then these equations are pretty accurate for the non-channel, like micrometer scale. But that is a very old technology. Micrometer actually is like 30-40 years ago. Today's transistors L is only like 20 nanometer or below. But in this course, we are going to only look at the non-channel devices quantitatively using those equations here. So any questions? So I've got one question here. Is it called linear because ID grows linearly with respect to VG? Okay, so that's a good question, but unfortunately the answer is no for this one. So I will explain. So why this is called a linear region and saturation. So we talk about saturation, okay, and then let's go back why this is called linear region. So the reason we call it linear region is when the small VD, okay, is very small. So this equation essentially is a second order equation. You have first order term, here you have this VD, and here you have VD squared. And you know, when the VD is very small, you can ignore the second order term and only keep the first order term. So if you do that, let's say you ignore the second order term, then only keep the first order term here. Then ID will be proportional to the VD. That means it's a linear function between the ID and VD. So that's why this is called the linear region. It's not because of VG, but because of the VD for the linear region. And we will talk about this point later when we look at the ID-VD curve. All right. Then one more question. Do these equations not work for today's MOSFET? I would say not accurately describe today's MOSFET, but to the first order, if you only look at the first order behavior, it's still true for today's transistor. But if you use those equations to calculate the exact current value, then it's not accurate. But this transistor still have those regions like linear region and saturation region. And we will talk about that in a few minutes towards the end of today's lecture. What is different in today's third channel device? Just stay tuned. Those equations are good for the long channel device very accurately, but for today's short channel device, let's say qualitatively, they are okay. But of course, the numerical values will be off. All right. Any other questions? Okay, let me stop for the first part.